Well, now that we've talked about electric potential energy and electric potential, let's discuss a unit you occasionally see, which is that of the electron volt, which is abbreviated little e, capital V. So let's look at this, looks like a capacitor here, which is what I have, which I have two charged plates, one at positive voltage, one at negative voltage, and we can see these equipotential lines in between. So we have it 0 in the middle, and they become more negative as you get to the negative plate, more positive as you get to the positive plate. And specifically, it's like plus 1 volt, plus 2 volts, etc. And let's go ahead and say we place an electron on this center line, so at the point where the electric potential is 0. Now, what would the electron naturally do? Well, it's going to, if we release it, it will accelerate towards the positive plate because it's repelled from the negative and attracted by the positive. And so it's going to gain some kinetic energy when it's released. Well, where does that kinetic energy come from? It comes from electric potential energy. So as it gains kinetic energy, it is going to be losing electric potential energy. The system is going to lose electric potential energy, and that'll be minus delta UE, which we can calculate with Q delta V, so minus Q delta V. And so let's say specifically we're going from this position here to this position here. Well, that is a potential difference of positive 1 volt, and the charge would be the charge of an electron, so that would be the elementary charge, which is 1.6 times 10 to the negative 19 coulombs, remembering that a volt is a joule per coulomb, so 1.6 times 10 to the negative 19 coulombs times 1 joule per coulomb gives us 1.6 times 10 to the negative 19 joules. I know that's cut off a little bit here, this just says joules behind us, so 1.6 times 10 to the negative 19 joules. Okay, nice and simple. However, a lot of times, we are not going to use joules, but instead we will employ a different unit that's basically defined by this exact context, which is an electron volt, 1 eV. So an electron volt is the amount of energy needed to accelerate an electron through a potential difference of 1 volt. So in other words, it was the amount of energy needed to get the electron to go from here to here to accelerate between these 2 points, which we just calculated was 1.6 times 10 to the negative 19 joules. So 1 electron volt is defined as 1.6 times 10 to the negative 19 joules. So once again, that's just from multiplying the charge of an electron by 1 joule per coulomb for 1 volt. Now, okay, a couple things here. First off, electron volts are not units of electric potential or of voltage. And that can be confusing because the word volt is in electron volt, but electron volts are actually units of energy because it's a charge times volts, so times a potential. You multiply those together, we get an energy. Additionally, this is really common in nuclear physics and particle physics. Essentially anything when we're using, like basically you're examining particles that have super tiny masses, protons, electrons, some combination of the above. Because these particles have such tiny masses and they move so quickly, well, their masses are so small though that the energies are typically pretty small. We're going to have, we've seen this consistently, we've gotten energies that are like times 10 to the negative 7, 8, 9, 10, even down to like negative 19, etc. And with all that scientific notation, it can be kind of annoying. So instead, a lot of times we'll use electron volts because that allows us not to have to deal with the scientific notation quite as much and just makes some of the calculations easier. So let's look at a brief example. So I've got two plates here, one at positive 300 volts, one at negative 300 volts. I've got these equipotential lines in between. I've labeled the values up here. And we have an electron starting at this 0 position. And let's say specifically, so we're going to call that position A, and we're going to say we have position B, C, D, and E. And we want to know what is the work required to move the electron from A to B, from B to C, from C to D, and then if we release it at D, so if we release it at this point, it's going to accelerate that direction. What will its final velocity be when it strikes, right before it strikes a plate at position E? Okay, so let's look at this for a second. So the work from A to B, well, we know that the work is the change in electric potential energy that we move it around here. So if I'm going from A to B, we could say, all right, well, that change in electric potential energy is Q delta V. And if we wanted to, we could stick in the charge of the electron and the change in voltage between A and B, which is minus 200 volts. But we don't need to do that. Instead, if we use electron volts, it's really simple, because I just look at this and go, okay, if I'm moving the electron from A to B, the system is going to gain energy. I'm going to do positive work because it's going towards a like charge, so it's going to be positive. And I've got one electron going across 200 volts. Oh, okay, well this is simply plus 200 electron volts. And I'm done. That's all I have to do, because this would be the amount of energy it would take me to move it to B. It would be 200 electron volts. So if I go from B to C, well, B to C is going to be what? 1, 2, 3. So it's going to be a change of 300 electron volts, and it's going to be a negative work because it's going towards a positive. So this is simply negative 300 electron volts, rather than having to do all the calculations with joules. And then same thing, if I go from C to D, I'm going to go 200 electron volts towards the negative, so that's going to be positive 200 electron volts. Nice and simple. All right, so let's say we release it at D, and then it's going to speed up and go to E. Well, how exactly can I do that? Well, let's first figure out what is the change in kinetic energy going to be. Well, that's going to be the negative change in electric potential energy. Whatever it gains in kinetic, it lost in electric potential. And if we look, that is 400 volts. Now, it would have been negative 400, but we have this negative here, so it's going to gain 400 electron volts of kinetic energy. But we want to know the velocity. So, okay, we look at this and go, all right, well, if we release it from rest, the initial velocity will be 0. I can do delta K. Usually I would have to subtract the initial kinetic energy, but if it starts at rest, that'd be 0, so it'd just be 1/2 mv squared. And I'll say, okay, 400 electron volts is 1/2, 9.11 times 10 to the minus 1 kilograms, v squared. And I could calculate v here. But this part would be a mistake. And the reason it's a mistake is because if we look at this equation, this is in kilograms, this is in meters per second, and you're going to square it. So this side of the equation would be in joules. So we actually have to get the left side of the equation in joules first. So if we're working with just like works or changes in electric potential energy or whatever, even if we're working on changes in kinetic energy, you can use electron volts. But when we start moving to like other measures like velocity, which is in meters per second, we need to put it back into joules first. So if I have 400 electron volts, well, that was 400, and we set 1 electron volt was 1.6 times 10 to the negative 19 joules. It's pretty easy to remember. It's basically the same number as the elementary charge. And so I just multiply those together, divide by 1/2, divide by a mass, take the square root, and I'm going to get this velocity of 1.2 times 10 to the 7th meters per second, which is incredibly fast. But once again, these are tiny particles. So this is exactly how you would go about doing something like this. One final point, what if instead of an electron, we had used a proton? So for instance, if I have a proton at position A, and I want to see how much work it takes it to get to position B, which I have on the 100 volt line here, well, okay, how can I go about doing that? Well, remember, work is change in electric potential energy. If I'm moving the proton towards other positive charges, that will be a positive work. So it's going to be positive. And, well, I could go and I could say, well, okay, well, the charge of a proton is 1.6 times 10 to the negative 19. And this is 100 volts. But once again, we don't have to. We can just say, oh, it's 100 electron volts. Because a proton and an electron have the same charge. They may have different masses, but the same charge. So really, when we defined an electron as the amount of energy it took to accelerate an electron through a potential difference of 1 volt, equivalently, that is also the amount of energy necessary to accelerate a proton through a potential difference of 1 volt. For that reason, we can really use either proton or electron pretty interchangeably when dealing with electron volts.